Today we're going to tackle a cubic lattice question where we're going to look at the theory where the question is we have nickel at all the corners of this cubic lattice, Ti at the center of unit cells. What's the empirical formula? What's the lattice shape? And then we have to do the calculation with this given atomic radius in this unit. And then we're going to find what is the edge length and the density. So we're going to do it all. So we're going to start with our problem. Ni is at all corners. So I would advise just drawing something out so that you don't get tripped by the reading comprehension. So Ni is at all corners. And then Ti is at the center of unit cells. It's plural, but it's saying at the center of unit cells. This is one unit cell, and it's at the center of many unit cells. This is then, we can tell that with nickel being at the corner, and nickel being at the corner is present only on every corner. It is not anywhere else. There is no nickel in the center, there's no nickel on the faces, so we can safely say that this is a simple cubic lattice structure. So if you paid attention, the center of unit cells, it does not say the center of the face of every unit cell. So be careful on that, because for face-centered cubics, there is like a little half an atom just lying on the face. It's a center, yeah, but it's not the center of a unit cell. So be careful on that reading here. How do you find the empirical formula? Well, anything that's on the corner is going to account for 1/8. Anything in the middle, sometimes there can be 3 or 4 stuff in the middle, will count as one whole atom. Anything on the side, the edges, is going to count for 1/4, and anything on the face, if it exists, is going to count for 1/2. And I'll use dark blue just to show that this does not exist, but if it does, it will count for 1/2. 1/2 for this one, and 1/4 for the edges. Okay. Now to get our empirical formula, we're going to use these fractions and count how many nickel there are. There are 8 nickels at each corner, and each corner counts for 1/8. So there is 1 net nickel in this unit cell. As for our Ti, we have 1 in the center, and that's it. So that's just going to give us 1 times 1. And notice how it's Ti, it's not TL. On the formula sheet, there's 2 things that look really similar, so gotta be careful on that. So since it's a 1-to-1 ratio, this would be your empirical formula. So that's a theory for you. Now, we gotta use what we have to find the edge length and the density. Okay. So I'm going to go over a little theory on how we could do that. So for any question, a density is the mass divided by the volume, and the mass consists of the mass of all the atoms present in that unit cell. So sometimes it's just one atom, which is really convenient, but sometimes it's a compound where here we have 2 atoms together. So you're going to use a molar mass of all the things which you have in that unit cell divided by Avogadro's number to get you the mass per atom. And then you multiply it by how many net atoms there are in that unit cell. And that is calculated by these fractional numbers. So in a simple cubic shape, it's only going to be 8 times 1/8. 8 times 1/8, which will give you 1 net atom. And where you have a body center cubic, it's going to be net 2 atoms. Where you have a face-center qubit, it's going to be a net of 4 atoms. So then in this situation, what we would do is our mass, what do you think? Would our mass be 1 or would it be 2? So actually in this case, it's only going to be 1 because we've already determined that our shape is simple cubic. Well, where did this come from? Okay. So we've already determined that our shape would be simple cubic. As we've gotten here, what was the lattice shape? We answered simple cubic. So that's why we're only going to use 1 for our calculation here. It's only going to be 1. So 8 times 1/8. So be careful, this part reflects the net number of atoms in that shape, okay? Even though in the bottom example here, we have 2 things going on here. We have 2 atoms technically, but we're only considering the net atom of that shape, which is only determined by the atoms at the corner, determined by the presence of the atoms in the corner. And since the atoms in the corner only exist in the corner, it's only going to be a simple cubic. And then we divide all of this by the volume, and the volume is the length cubed. Sometimes instead of giving you atomic radius, they'll just give you the length, the edge length, so then you can just cube it to get your volume, no biggie. However, in this situation, something is more complicated. So to finish up our little theory here though, before we do the calculation, on your formula sheet, they will tell you the relationship between length and radius for BCC, FCC shape, and simple cubic, which is convenient if your cubic lattice only has 1 atom. Then you would just substitute the radius for the radius of that atom. But in what we have in this question, we have 2 atoms, so we cannot just sub in our radius into these equations. So then we have to understand what our equation is telling us. So for simple cubics, it's gonna be the same. It's just gonna be 2r. It's very simple. Just look at this diagram, you'll get it. For face-centered cubics, so face-centered cubics, how they derived this formula is given the side view of this face-centered cubic. We use Pythagoras, and then we can tell, just using Pythagoras, we can tell that this part all makes sense. So having derived this part, we can then do some dividing and cubing and square rooting to get this. But this 4r is assuming that all of these atoms are the same atoms, so all of these lines would have the same radius, which is not the case in our situation. So instead of just going by 4r, we're gonna think about how this r is consisting of 2 of the atomic radius of one atom, and 2 of the atomic radius of the other atom. So then it's gonna be and that would be the relationship between length and radius. And as for a body-centered cubic lattice, which is a question we have, it's a little bit more complicated given that there is like a 3D cube thing. However, so usually they would just do something complicated like this, but what gets important is this part. Instead of saying the length is made up of 2 radiuses plus 2 radiuses, and then saying that it's going to just be 4r, because if we're assuming that all of these atoms are the same, all these r's would be the same, so we could just say 4r. But we can't do that if we have different atoms in the cubic lattice. So instead of saying 4r, we're going to have to say that the radius, in relation to length, the radius is made up of the 2 radiuses of one atom and the 2 radiuses of the other atom. Okay, now we're gonna do our sample problem. Okay, so we're gonna find the edge length before we can find the density. Actually, let's just do it here.